Hi, this is Michael Wan, here to present the paper Mutual Information-Based Knowledge Transfer under State Action Dimension Mismatch. This work was done at the University of Illinois at Urbana-Champaign with Tanmay Gangwani and Professor Jian Peng. First, let's dive into some motivation. Reinforcement learning is notoriously sample inefficient. We often require millions of samples to learn a good policy for just a single task. This is exacerbated by the fact that in many cases, environment interaction can be expensive, such as with robots in the real world. Transfer learning is one approach towards solving the sample inefficiency problem. In this work, we assume access to a pre-trained teacher policy trained in a source MDP, shown in blue, with the goal being to train a student policy in the target MDP, shown in orange. Ideally, the teacher should accelerate the learning process of the student, which would indicate successful transfer. Prior work has considered the setting where the state and action spaces have been the same across source and target MDP. But what if this isn't the case? How should we handle the difference in state space? And how should we handle the difference in action space? Our work seeks to devise a transfer learning method that gracefully handles these differences. We now address the first question. How do we handle the difference in state space? The answer is we do this through a learned embedding space, which acts as a conduit between state spaces. Our learned embedding space is parameterized by an encoder function phi. Importantly, we force the dimension of the embedding space to match the dimension of the state space in the source MDP. Because of this, we can now use the teacher networks for transfer. At each time step, we pass the current state into our encoder, and this embedding is passed to the teacher networks. We train our encoder to adhere to two properties. First, we require that the embeddings be task-aligned, so our encoder is trained to maximize the cumulative discounted rewards in the target MDP. Second, we require that the embeddings have high correlation with the states in the target MDP. To this end, we maximize the lower bound on the mutual information between state and embedding. The lower bound consists of an entropy term and an expectation term involving a variational distribution, which consists of a neural network that outputs the mean of a multivariate Gaussian and the learned diagonal covariance matrix. Note that we can omit the entropy term from our mutual information loss term, since it is a constant with respect to our parameters. Now we address the second question. How do we handle the difference in action space between the source and target MDP? We do this through knowledge transfer in the hidden layers using our learned embedding. The main idea is to augment the student representations with teacher representations. We feed the current state into the student networks and the embedding into the teacher networks, and at each layer, we take a weighted linear combination of the student and teacher pre-activations, as seen in the figure to the right. Crucial to this knowledge transfer are the mixing weights. Lower values indicate a heavier dependence on teacher representations, which implies that the teacher knowledge is useful for achieving the target task. Although the student can rely on the teacher during training, we utilize a coupling loss that forces the student to be independent of the teacher by the end of training. The figure shown here shows the interplay between our embedding space and knowledge transfer. Note that our method, which we refer to as MIKT, can be incorporated into any RL algorithm. In this case, we use PPO. Our complete algorithm is as follows. We update our encoder using a loss function consisting of two terms. First, a mutual information loss, and second, the RL loss. We update the student policy and value function using the RL loss, update the variational parameters using the mutual information loss, and update the mixing weights with the loss consisting of the coupling loss and the RL loss. We experiment using ant and centipede tasks from Mujoko, with the centipede tasks differing in number of legs and disability. We experiment with scenarios such as transferring from four-legged centipedes to six-legged centipedes, and transferring from centipedes to ants. We can see that our method, shown in blue, drastically outperforms the baselines on the given tasks. A natural question to ask is whether we need both the RL loss and the mutual information loss to train the encoder. We experiment with removing both of these terms in succession and find that both are necessary components, although training the encoder with just the mutual information loss also achieves good results. We also investigate the effect of task similarity on our method. We experiment with transferring between centipedes as opposed to transferring knowledge from a hopper to a centipede, and find that, as expected, transfer between centipedes results in higher reward, and that the teacher influence is much greater in the cases where the source and target task are similar. In conclusion, the main takeaway is that we present a transfer learning method that works with MDPs with different state and action spaces. We do this through a learned embedding space and knowledge transfer in the hidden layers. To the best of our knowledge, our work is the first transfer learning RL work to address the state and action space mismatch across MDPs, and we hope that future work will be done in this area. Thank you for listening.